we're going to start the repeated eigenvalue. For example, 1, solve y prime equal to 1, negative 1, 1, 3, y. I'm going to show you the long way y, the repeated eigenvalue, and then later on I will summarize how should you do it. So for solution of the homogeneous system is actually when we assume y, the solution of the y is actually exponent lambda t, as what we have learned in the homogeneous system. For the first case where you get the real and different eigenvalue, and this is a system of y prime equal to ay. So when you substitute equation 2 to the homogeneous system y prime equal to ay, so your y prime is actually, you differentiate the y respect to, assume let's say y is dependent on t, so your y prime, it will be your dy dt. So b is a constant, so you only differentiate respect to t. So you get lambda b exponent lambda t. Then you plug in the y prime into here, and the your y prime, you plug in the y prime will be lambda b exponent lambda t. And then the y we already assume is b exponent lambda t. New equation. Basically, we have the system y prime equal to a1. And we assume the solution y is actually the eigenvector multiply exponent lambda t, where the lambda is your eigenvalue. So the y prime is actually lambda b exponent lambda t. So you plug in these two into the homogeneous system. You get lambda b exponent lambda t equal to a y already assumed as b exponent lambda t. And then we may cancel the exponent lambda t at each both hand side. So we have actually after we cancel here, we have ab minus lambda b equal to 0. B cannot be equal to 0 because we already assumed the solution will be a constant eigenvector multiply exponent lambda t. So that's why I cannot cancel out the b. So since kb cannot be equal to 0, eigenvector b cannot be equal to 0. The only possibility is to let a minus lambda I equal to 0. By solving determinant of a minus lambda I equal to 0, if a is 2 by 2, you will get lambda 1, lambda 2. And then before the semester break, you have since you have two real and different eigenvalues. Today we are going to see where you have lambda 1 equal to lambda 2. So this is a homogeneous system. First step is actually you obtain eigenvalue by letting a minus lambda I equal to 0. You may on the y. So this is the reason. After you letting a minus lambda I equal to 0, you obtain your eigenvalue. You plug in back your eigenvalue, you obtain your eigenvector. So then with the eigenvalue and eigenvector, you obtain your solution of your y. So now we are going to look at y prime equal to 1, negative 1, 1, 3. Okay, and the notes here you can refer to your author, learning material, chapter 3. For example, we have this one. Y prime equal to 1, negative 1, 1, 3, 1. So we are going to solve y prime equal to 1, negative 1, 1, 3, 1. So solving this homogeneous system is actually we want to solve for the y. So first step, we are going to find the eigenvalue. Find the lambda 1, lambda 2. Okay, how to find lambda 1, lambda 2? Okay, let's determinant of your a minus lambda I equal to 0. Okay, where the I here is an identity matrix. So determinant is straight line. So from the matrix A here, okay, 1, the main diagonal you just minus with the lambda. 3 minus lambda, then equal to 0. We have 1 minus lambda times 3 minus lambda. So minus the product with the other diagonal. So minus with negative 1. Remember how you calculate determinant. Product of the main diagonal minus with product of the other diagonal. So be careful of your sign here. Minus with negative 1 equal to 0. And then expand it carefully. Because if you do it carelessly, then you reflect your lambda 1, lambda 2, and so your V1, V2. So expand it carefully. So you should have, this is 3 minus lambda minus 3 lambda plus lambda squared plus 1 equal to 0. Lambda squared with, so total is minus 4 lambda plus 4 equal to 0. Where you have this lambda minus 2 power 2. Where you have lambda 1 equal to 2, lambda 2 also equal to 2. So now you have repeated eigenvalue. Same eigenvalue. So step 1, finding the eigenvalue, you obtained already. Now step 2, find first eigenvector, find V1. Okay, how to find the V1? How to find V1? Remember in beginning, okay, from here, to find V1, substitute back, okay, lambda 1 that you obtain into here, homogeneous system here, A minus lambda I, V. Okay, so when you replace lambda by lambda 1, so this will be V1. So by solving A minus lambda 1 I V1 equal to 0. Okay, so taking back your determinant just now, this is straight, so make it become matrix. You just change it to round. Where you have is actually, so this is 1 minus, okay, lambda 1 is actually 2. So 1 minus 2. And then this one, negative 1, 3 minus 2. So V1, let it equal to X and Y equal to 0. So simplify it, you have negative 1, 1, negative 1, 3 minus 2 is 1, x, y equal to 0. Okay, you notice that if row 1, okay, row 1 you multiply by negative 1, put back to your row 1. Then you have actually 1, 1, 1, 1, x, y equal to 0. So hence you have two unknown x and y but reduced to only one equation. Because now you can see that after you multiply row 1 by negative 1, row 1 is actually equal to your row 2. Means you left only one equation, which is x plus y equal to 0. So in this case, you can let x equal to s or y equal to s, either one. So let's say I let, okay, because x plus y equal to 0, so I let x equal to s, then y will be equal to negative s. Or the other way, you may let y is s, then x will be negative s. That's why you have infinite many solutions. Because you got two unknown but only left to one equation. So in this case, my xy is 1, negative 1, factor out the s. So v1 is obtained by letting s equal to 1. So I have 1, negative 1. Okay, we may have another variation is if you let y is s. So negative 1 and positive 1. So it obtains your v1 already. Okay, now how to obtain your v2? Okay, first of all, I will tell you the reason, and then later on summarize. Okay, so next one, when you see the repeated eigenvalue, you can straight away using the formula. Okay, and remember in second order differential equation, okay, second order homogeneous differential equation, right? When you have the repeated same and repeated m, remember that, okay? For example, this one, remember that here. If this is the second order second order homogeneous equation, let's say your m1 equal to m2 equal to 0, then you say your solution of your y is actually equal to 2. You say your solution is a e 2x. Okay, and then you put b e 2x. A and b clash. That's why you need to multiply here by x. Or we simplify a plus b x exponent 2x. So now we have the same eigenvalue, Okay, can we follow the same pattern? Here we have the first solution here is actually for solution of your homogeneous system. This one we solve for y. Our pattern is actually a v1 exponent lambda 1 t plus b v2 exponent lambda 2 t. Okay, this is what you learned in the last I think last week before your semester break. If you have real and different eigenvalue, so your solution for a homogeneous system will be a v1 exponent lambda 1 t plus b v2 exponent lambda 2 t. Okay, now lambda 1 equal to lambda 2. It will look like here, same. We have the same, this one is same m, this is same eigenvalue. So can we just multiply v2 here by t? Can we just multiply v2 here by t? So now I'm going to show to you. Let's assume your y is v2 t exponent lambda t, because we got same eigenvalue. So we assume, okay, the second solution y2 here is v2t exponent lambda t. Then the y prime you will have, okay, you need to use the product rule because this is q, this is p. So you have q, which is v2t. Then you differentiate the v, you have lambda exponent lambda t plus v du, exponent lambda t, differentiates the u, you get v2. And remember, okay, you ddt uv. You got u v prime plus v u prime. So this is a u, v2t, differentiate the v, you got lambda exponent lambda t plus v, which is exponent lambda t, differentiates the u, here you get v2. And the v2 is constant eigenvector. So this is our y prime. So plug into the homogeneous system, plug in these two things into the homogeneous system, y prime equal to ay. So y prime is here, you got v2, okay, lambda t exponent lambda t plus v2 exponent lambda t equal to ay. Okay, y is here, a v2 t exponent lambda t. So now, okay, if you assume y equal to v2t exponent lambda t, why we assume this way is actually we follow, okay, the pattern of second order homogeneous equation. Since we have repeated, okay, m, okay, here we multiply by x, so no longer clash. So how about this one? Can be just v2 here multiplied by t. So we are going to check whether this, okay, this way is possible or not. Okay, and then just now also we will cancel out this one, but we cannot cancel out the v. If we cancel out v2, because v2 cannot be 0, also cannot be cancelled out. We want the solution in terms of v2. Okay, so what we are going to compare is actually if we compare this term, select together this two term. So we have a e2 t minus v2 lambda t equal to 0. Okay, another one is here, v2 equal to 0. Okay, and for this one, I can factor out, okay, the t can be cancelled. So the t and cancel the t. I got a v2 minus lambda v2 equal to 0. And I factor out a minus, okay, multiply by I because a is matrix, lambda is a constant value. So you want to do metric operation, so I must multiply here by an identity matrix. So when you arrive here, a minus lambda I v2 equal to 0. If you put back the same lambda eigenvalue just now, lambda which is equal to 2, we obtain back the same, okay, this one, a minus lambda I v2, a minus lambda I v2. Because lambda 1 equal to lambda 2, when you solve here, your v2 you obtain the same. v1 will be equal to v2. If we solve this one, later on we'll get v2 is actually equal to v1. If v2 equal to v1, we have only one solution. Here, v1 here same. Okay. Besides that, from here we have actually two terms. One term is actually here. Another term here will say that v2 equal to 0. If v2 equal to 0, then this solution not exist at all. So means we have contradiction. One said v2 0, another one v2 equal to v1. That's why this way, in the solution that we assume like this, y equal to v2t exponent lambda t is invalid. And then what we are going to do, we assume in the correct way is actually assume your v2 equal to v1 times t exponent lambda t plus v2 exponent lambda t. Okay. I'm going to show you. In the correct way is actually assumes y is v1 multiply t exponent lambda t plus v2 exponent lambda t. So here again you differentiate y prime. So this one using product rule, you get v1 t. So lambda exponent lambda t plus, this is exponent lambda t, this is 3, plus lambda v2 exponent lambda t. Okay, using the product rule, this is u. Okay, this is v prime, and then this is v, this is u prime. And v2 exponent lambda t, you get lambda v2 exponent lambda t. This is 1, 2. Okay, so plug in these two now into your y prime equal to a y. Y prime equal to a y. So y prime is this one. We have v1 t lambda exponent lambda t plus exponent lambda t v1 plus lambda v2 exponent lambda t equal to a y is actually v1 t exponent lambda t plus v2 exponent lambda t. And then okay, we can cancel out the exponent lambda t. And then how are we going to compare? We are going to compare the same term with v1t. Okay. v1t and v1t. So v2 of v1. This is v1 only. Okay. And then this term. So first of all, we compare the term here. A v1t, okay, this one minus v lambda v1t equal to 0. Okay, and t cancel out. Now you cancel out the t, so you got a minus lambda I, 1 equal to 0. So this one, okay, from this equation we can obtain lambda 1, where we have obtained already. Now we are going to solve this one, where I put it into the squared term, already highlight it. This one. So we have here actually lambda v2 plus v2 equal to v1. v2 this term v2 minus lambda v2 equal to v1. This one got a plus a y, so a minus lambda I V2 equal to V1. So now, okay, we got here, if it assumes, okay, the second solution is actually y equal to v1t exponent lambda t plus v2 exponent lambda t, we arrive at two different equations. One is actually a minus lambda I v1 equal to 0, where we can use it to solve for v1. And to get the v2, we have a minus lambda I v2 equal to v1. So means, okay, here this is all the derivation and the theory y. For repeated eigenvalue means, okay, so I will summarize again. To solve, okay, this y prime equal to 1, negative 1, 1, 3, y. So this is a homogeneous system. First step, you find our eigenvalue by letting determinant a minus lambda I equal to 0. And we get this repeated eigenvalue. So second step, you find v1 as usual by solving a minus lambda 1 I v1 equal to 0. And to get your v2, you have to solve a minus lambda I v2 equal to v1. Okay. And if you say y must using this way, this is the reason, and y cannot assume, okay, your second solution is v2t exponent lambda t, because through the derivations here, we got two contradicts, exactly v2 0, and then if you solve this one, actually you get back v2 equal to v1, and then here another one v2 0 contradicts, so it's impossible. That's why we have to assume y is actually v1t exponent lambda t plus v2 exponent lambda t. Hence, okay, to get the v2, you have to solve this one. Step 3. Okay, you have to solve, find the v2. Okay, find the v2 from a minus lambda I v2 equal to v1. So recall back what is the a just now. Okay, it's actually from step 2, you can easily, okay, this is a minus lambda, okay, lambda 1 equal to lambda 2, so you get the same, okay, system, but however, the right hand side, you just replace it with your v1. Because step 2 is actually you solve a minus lambda 1 I v1 equal to 0. For repeated eigenvalue, lambda 1 equal to lambda 2. So means, okay, when you compare for repeated eigenvalue, your step 3 is actually you solve it, you find v2 by solving a minus lambda. Okay, lambda 2 equal to lambda 1. I v2 equal to v1. So everything will be same except the 0, you equal it to your v1. Okay, so you will get step 3. So it will be same. So 1 minus I got right. Having problem. Suddenly I couldn't write. Because it came back to the word. But word also having problem. Not good, okay. So the step 3, because previously writing in my word it got very long here, that's why I changed to the H to right and suddenly the H cannot write. Step 3, we find V2 from A minus lambda I V2 equal to 0. Okay. And let's take the A, our A here, we got 1 minus lambda, our lambda is actually 2. So this is 1, this is negative 1, so 3 minus 2. V2 also we let it equal to xy. Okay, this is V1 for repeated eigenvalue A minus lambda I V2 equal to V1. Because if we let it equal to 0, then we obtain V1 equal to V2. Okay, what is V1 that we obtain?
One and negative 1.
Yeah, negative 1 and negative 1. So that 1, negative 1. Okay, then you simplify it, negative 1, 1, negative 1, 1, xy equal to 1, negative 1. Okay, just now we row 1 we multiply by negative 1, right? Then we put it to row 1. So we use the same operations. So you get 1, 1, 1, 1, xy. So negative 1, negative 1. So again, you can see row 1 equivalent to row 2. Row 1 is equivalent to row 2. Okay, so you can pick up any row because they are the same. So we have x. Okay, I hope you understand. This is a matrix multiplication, row and column. So 1x plus 1y. So x plus y equal negative 1. Okay, for repeated eigenvalue, it's very important you make the same assumption. If just now you let x equal to s, in finding your V2, you must also let x equal to s. This is only for repeated eigenvalue. Okay. So now you have to make the same assumption, x equal to s. Okay. So your y will be negative 1 minus s. And then you put back your xy. Okay. You break it into a vector dependent on s and a constant vector. So x is only 1s, no constant value. Okay, y is negative 1s. Okay, constant is negative 1. So you can see that you must use the same assumption so that the vector that dependent on the s will be equal back to your v1. If you don't use this pattern, it won't get back nice. So I repeat one more time. Okay, to find the V2 for repeated eigenvalue, you solve A minus lambda I V2 equal to V1. In just now my derivation, all that you can just for your understanding, but to solve it, you can to solve this one, these equations, solve this homogeneous system. Your written answer, first step, finds your eigenvalue by solving determinant A minus lambda I equal to 0. Okay, and then you get repeated eigenvalue. So V1 as usual is solve A minus lambda 1 I V1 equal to 0. And for V2, for repeated eigenvalue, you solve A minus lambda 2 I V2 equal to V1. Okay, all the long derivation are just for your understanding and why the formula like that. Okay, and then another hint. When you arrive at the equation, you must make the same assumption. If finding V1 you let x equal to s, here you must maintain x equal to s. This for repeated eigenvalue only, so that we can get nice back the vector that dependent on s is back your v1. And the new constant vector this is actually your V2. Okay. So now, okay, what is the solution? The solution is actually y equal to a V1 exponent lambda t plus b, okay, b. Okay, remember just now we assumed okay, the solution is this way. We assume here. This is actually the second solution. This one is actually your this is your y2. V1t exponent lambda t plus V2 exponent lambda t. So B, you have V1t exponent lambda t plus V2 exponent lambda t. So V1, 1, negative 1. Okay, V1, okay, as usual, we okay, just take by taking s equal to 1. So this is a V1. Lambda is actually 2. B, 1, negative 1. This is multiplied by t. This is exponent 2t. V2 is 0, negative 1, exponent 2t. This is y. Okay, y actually we have the y1, y2. Okay, if you want each of it y1, pick up all the first row. So a exponent 2t plus b 1 times t times exponent 2t. So b t exponent 2t, and then have this. Okay, this is 0 times here, so 0. For y2, take the second row. y2, negative 1 times a times exponent 2t, so negative a exponent 2t. And then okay, second row here, so negative b t exponent 2t. So negative b t exponent 2t. So negative 1, negative exponent 2t. So this is y1 and y2. Okay, if given the initial condition, if let's say given t 0, okay, y1 equal to 1, y2 let's say equal to 1, then you can solve for your a and b. You can solve for a and b. So then you can get your particular solution. So okay, I conclude back okay, for repeated eigenvalue. Repeated okay, eigenvalue. Okay, first step, okay, you solve a minus lambda I equal to 0. You obtain lambda 1 equal to lambda 2 equal to lambda. Second step, okay, you solve a minus lambda I v1 equal to 0. Okay. Third step, okay, you solve a minus lambda I v2 equal to v1. Okay, and another hint is, if let's say here you use x equal to s, so when solving in step 3, you must also use the same thing, x equal to s. If here you use y equal to s, when solving v2 also you must maintain y equal to s. You cannot change. If you change, you won't get the nice pattern as this one. And then you will break it. For example, you get like this one. So your break it a vector dependent on s and a vector which is constant vector. So letting s equal to 1, this will be always your v1. The constant vector is always your v2. So lastly, your solution is actually in the y is a v1 exponent lambda t plus B1 multiplied T exponent lambda T plus B2 exponent lambda T. So this is for repeated eigenvalue for the case of two simultaneous first order differential equation where in each case your matrix A is a 2 by 2. So is there any questions that you want to ask me? And the notes you can get here from the author.